Hello. We're going to review Chapter 6 as the previous recording had no audio, so thankfully I have been able to fix it. So we'll go over that chapter again with audio. The objectives are important. As I've always said, this really guides your study and tells you what's important. We'll do the conservation of mass principle and use it for different steady flow control volumes. Apply the first law of thermodynamics for conservation of energy. Identify energy carried by fluid streams and control surfaces. The sum of internal energy, flow work, kinetic energy, and potential energy. And then we will solve some energy balance problems for common steady flow devices, such as nozzles, compressors, turbines, throttle valves. There's mixer heaters and heat exchangers that you need to review for some of those problems and study the examples. So, having seen the objectives, let's start with the conservation of mass. Whenever we talk about the conservation of mass, of course, if we have 2 kilograms of something and 16 kilograms of another, the total mass should be 18 kilograms of the substance. In reality, sometimes there's a small mass change due to energy changes, but it's negligible. So we'll be using that principle of conservation for mass. So this is an example of a conservation of mass. Let's say here initially, you're putting 20 kilograms of water and there's 30 kilograms going out, then you will have 20 kilograms of water accumulating. So expressed in a different way, what we're saying is the change in mass with time is going to be equal to the total mass, and we're going to use this summation of mass going in during that interval of time minus the summation of the mass going out for that interval of time. And of course, this change in mass with time is that we call m dot. Expressed in a more generic way, we're going to see how, whenever we're talking about the mass, changing mass, and CV means control volume, which is what you establish for your calculations. It's going to be equal to the integration of this density times CV over the control volume. And if we look at the dimensional analysis, we have density, let's use SI units. Density is mass over volume. And if we use kilograms per cubic meter, so if you have density and you multiply times volume, of course, we have mass for, let's use kilograms per cubic meters. In fact, that I would be using SI. So you have the mass. So this is the total mass over that control volume. If now you want to see the mass, the change in mass with time, you have to get the derivative of this integration here. And basically, this would be in cases where there's an equation rather than a fixed number. And so this is the same concept as we were talking about. So this summation of mass in minus the summation of mass out, this is the change in mass within that control volume. So this is the equation that you need to remember. and this will establish again as the change in m dot over the control volume. Whenever we have what we call in engineering steady flow processes and in thermodynamics, in a steady flow process, as we discussed in this class, it means two things. First of all, that we have a mass within the control volume that is constant. Since the mass is constant, that means that the change in mass over time is zero, but the mass is constant. So that means that since the change in m dot, or the mass of time within the control volume, is constant, then the summation of the mass per time going in equals the summation of mass per time going out. And remember, all of this is within the control volume. In Blackboard, you have copies of this slide, so I encourage you to practice this type of problem. And it's there. Make sure you practice. Let's give you a couple of definitions here. We've been talking about the velocity, but I just want to emphasize, and we will see this in hydraulic engineering, that the velocities that we've been using are the average velocities. Because in a pipe, like in this one, for instance, what you have is, this is as if it was an equation. So this is giving you the velocity profile with distance. And if this is the pipe, what you see, this would be the radius. And of course, this is the diameter. So whenever you are close to the surface of the pipe, and this is three-dimensional, remember, what you have is that the velocity changes with distance, with radial distance. And the velocity would be maximum right at the center line of the pipe, where that distance would be equal to the radius. And then at the edges, and we'll see this in hydraulic engineering, it's called the no-slip condition, velocity along the surface of the pipe is zero. So whenever we're talking about velocity, well, what velocity are we talking about? Well, it's really the average, because if we were to do it specifically with the exact velocity, it would change. So basically, this would be an average value, which would be sort of like an integration of the velocity along the pipe, the radius of the pipe. This would be like Vm, this velocity profile here, times the area. So that's what we have as average velocity. What you need to remember also is that velocity times area is a volumetric flow rate. And I'll put this here. So velocity, let's say that it's meters per second, and the area is per meters. As you can see, this would be cubic meters per second. So this is the dot. So we'll be hearing some concepts that are extremely important. And again, this summarizes what I just said. We have an average velocity and the volumetric, or the volume flow rate. Remember, in the book they use italics. So in order to differentiate between velocity and volume, what I have been doing is having this V bar that is different from velocity. So if it's just the V, it's velocity. Whenever we look at the mass rate then, and we're doing some calculations with the average velocity, and that equals raw V times A. And as we said before, this V times A is the volumetric flow rate. So this would be, well, times the volumetric flow rate. If we do a dimensional analysis, let's say that it's Fi, the density is kilograms per cubic meters, and I multiply times cubic meters per second, so I have kilograms per second, which are the units of m dot. So this is the derivation of the expression. Now remember that in the case of gases or extreme temperature changes for water, instead of using a density of 1,000 kilograms per cubic meters or 1 kilogram per liter, you will find in the tables for thermodynamic properties the specific volume. So that would be like a lowercase v. And what happens is that the units for this, instead of kilograms per cubic meter, so cubic meters per kilogram, which is the inverse of the density. So whenever we look at m dot, with here, you have rho times the v dot, and then this is the specific volume. So instead of being multiplied by the density, then you have m dot is equal to v dot divided by the specific volume. Okay, and this is from table. So again, this is just reviewing what we just said, and sometimes I like to be redundant, so let me do this so that you're aware of the differences, and of course this is the velocity. Now there's no such thing as volume balance. We only can do mass balance. But if the density of the fluid does not change, the input, the output, and the fluid within the control volume, if they all have the same densities, then you end up doing sort of a volume balance, but it doesn't exist. So let me give you an example. Let's say that you have here a control volume, and you have here an input and an output, and then I have the density 1, and this is the density 2, which is equal to density 1, and I have a volumetric flow rate, or volume flow rate here in 1 and in 2, and I have a pipe that has an area 1 and have an area 2. When I do the summation, if it's steady state, we have a summation of m dot in equals the summation of m dot out, and so we have rho 1 v1 v1 equals rho 2 v2 v2, and if the densities are equal, what we're looking is at the volumetric flow rate. So it's equal to that. So this would happen, this relationship of having equal densities usually happens when we have incompressible fluids. Incompressible fluids like water, if it's incompressible, but let's say that you're very concerned about differences in density due to temperature, like thermal solution, in cases like that, we will not assume that the density is the same. We'll go by the book, because those differences in densities will tell you where the highest temperatures are, because hotter water will be lighter in general. So we already did this derivation. I encourage you to do example 6.1, and we did this in class as well, but make sure you understand it. It's a very important example. And this is reviewing some of those concepts. We talked about the mechanical energy of a flowing fluid. And this is very important to understand that whenever we say mechanical energy, refers to that portion of the energy that can be put to work. So we saw how mechanical energy, and in this case we have E dot, capital E, means the energy. The energy, remember, for the SI system is joules. If we have metric, we would have pounds per feet. But in this case, then we have the E dot, which is M dot times E, and the E is lowercase. So you get, this would be energy. If it's E dot, it's joules per second, which is watts, and this is power. And if we have lowercase e, is the energy per mass, so we would have something like joules per kilogram. So this is the lowercase here, and what you have is basically this same expression without the M dot. But we're mostly concerned about changes. So you can rest assured that most times I will not be asking about the total energy, at least for this chapter. We'll be looking at differences in energy. Because this difference in energy between 2 points, and here we have point 1 and point 2, is the change in energy that will either be lost and you need to provide, for example, with a pump, or the change in energy that is going to be an increase, in which case we can use it to convert it to work, like in the case of the turbine. And again, the notation remains the same. The change in energy, lowercase e would be per kilogram, and once you multiply times m dot, remember then it's energy per time. So let me just real quick do this dimensional analysis. So if I have kilograms per second and multiply it times joules per kilogram, so I have this per second and this is watts. Now in this chapter we introduce the concept of total energy. So now we're not looking at just the portion of that energy that can be used for work or usable work, but we're talking at the total energy, including the internal energy that before we said is really not usable for mechanical purposes. Now, whenever we talk about the total energy, that has to be included. So the generic equation is this one here, and one important aspect is the notation that the book uses for this total energy, using this theta. And for a flowing fluid, we need to incorporate pressure and volume. So we have the internal energy plus pressure and volume. This is the enthalpy. So we talk about the internal energy, and you can show it in the two different ways. The long expression, P, V, and then U plus KE, kinetic energy and potential energy, or S enthalpy. And of course, it's easier to go with enthalpy since in the tables you have both the internal energy and the enthalpy. just use the enthalpy directly, and then you have velocity and this part. So in the case of a non-flowing fluid, we have internal energy. And let me use the color here. So we have internal energy. In the case of a flowing fluid, instead of internal energy, you need to add to that the flow energy. And so this is what you see the enthalpy. So you have 1, 2, and 3 parts for the non-flowing, and 1, 2, 3, 4 for the flowing fluid. You'll remember in open systems we have energy input and output. We can have output as heat and work. So we can have Q out and work out. We can have energy and work going in. So we can have Q in and W in as well. And also we have energy of mass entering or leaving the system. So really this expression is the only thing we have left to discuss in terms of closed and open systems. In the case of a closed system, you don't have those. So we talked about the closed system, and the change in energy is due to Q and W, because there's no mass going in and out of the system. So that energy transferred by mass is this total energy, okay, M times zeta. Okay, so here we have M and enthalpy, velocity, and so this is the kinetic energy, this is the potential energy, and then this would be the internal energy of the enthalpy of flowing fluid. Whenever we're talking about the amount of energy, this would be just joules, and then this would be joules per second or watts. Remember, it's not kilowatts, it's not kilojoules, it's watts or joules. So, let's move on. Now we're going to incorporate our mass balances and our energy balances. Remember, we're talking for steady, and this can be kilowatts, it can be watts. It says kilowatts here, but it can be in units or BTUs or horsepower. So if this is the case of the change in energy, in this case around the control volume equals 0. So now we're going to do the energy analysis of steady flow systems. And steady flow systems, we just do a control volume around the system itself that we're going to look at. So we have a control volume, and we have mass in, mass out. It can be 1 in, 1 out, like in this case. It can be 1 in, 2 out, or it can be anything. So we can have a number of different inlets and outlets. So combining them, the expressions for the steady flow and steady state, we do now the energy balance for the open system. And remember, you can have Q in, W in, Q out, W out, and then this expression here would be the energy in carried by mass going in and out, and this is the out, and this is the mass going in. So now we have completed the description for each one of these variables. And as expressed earlier, that energy, total energy here for flowing fluids, is this one here, and you have to do this for each inlet. And remember, the M dot for each inlet can be different, and the N dot for each outlet as well. So an inlet and outlet. So this is the generic equation, and I would say this slide is the most important slide to remember for all your calculations. One of the things, again, here's a summary in and out, so this slide is important for you to understand as well. And in the book they mentioned different notations. I prefer to use this so you don't have to worry about positive or negative. But if you have to absolutely worry about positive and negative, this is the expression here. So you have Q and W, Q minus W. And what we have is Q net. If you have positive Q, then you have heat going into system. If you have negative, it's reduced. The work, then the same notation. If work is done on the system, that's adding energy in the system, work is negative. And if the system does work is positive following that notation. But you don't have to. I would say just stick with this expression here. But you need to understand that if I ask if it's a positive or a negative, then you go back to the original notation, which is the notation we use for closed systems. So let's mention some steady flow engineering devices, and we'll talk about components such as turbines, compressors, heat exchangers, and pumps. These components are part of power plants, and since they operate for a long period of time, these devices can be conveniently analyzed as steady flow devices. So nozzles and diffusers work together because the analysis is the same, except the nozzle is a device that increases the velocity. Just think of the nozzle at your house or for the hose. And as we mentioned in class, it's at the expense of pressure, because the relationship between velocity and pressure is kind of opposite. It's not directly proportional, but because the velocity is, v squared and the pressure is not. But if you have a decrease in, an increase in velocity, that means that the pressure goes down. And a diffuser does the opposite. It reduces the velocity. So here you have reduction in velocity, so it will increase in pressure. So what I want to do is to develop the equations for each one of those systems. And I'm doing this so that you understand what kinds of analysis you have to do to not just for this steady flow systems, but for other systems other than the ones that we will discuss. So whenever we talk about the diffuser, and because this is a basic thermodynamics course, I will give you some additional hints. Like in this case, I'm going to say it's a diffuser, it's insulated, or I would say adiabatic, meaning that Q equals 0. So this is the expression that you'll write over and over again, and then determine what can be done. So since it's adiabatic, then I have the Q's are eliminated. Now, the question of work. You ask yourself 3 questions. Number 1, is there a shaft going in or out? Is there electric wire? Is there a spring? These are examples. There's other questions, but these are the 3 most common ones that we'll see in class. In this case, we don't have a shaft. We look back. We don't have a shaft. We don't have a wire. We don't have a spring. So there's no work. It says that there's no elevation difference. So in this case, the Q is 0, okay? 0, and the work is 0, and it's 0. But for the case of elevation, they just cancel out because it's the same elevation. So in the end, the expression that I'm left with is as follows. This is the expression that I'm left with because this are zeros, okay? So if you have one inlet and one outlet, the law of conservation of mass, remember, if we talked about the change in M in the control volume equals 0, right? So we have M1 equals M2. And if M1 and M2 are equal, this will also cancel. So I will be left with enthalpy 1 plus V1 squared over 2 equals H2 plus V squared 2 over 2. And the analyses are very similar. So study example 6.4 of your book. And then turbines and compressors. And we have seen turbines. The turbines drive the electric generators in steam, gas, or hydroelectric plants. And the example we saw was for hydroelectric plants. So the fluid passes through the turbine. Work is done against the blades, which are attached to the shaft. And as a result, the shaft rotates and the turbine produces work. Now, whenever we talk about compressors, as well as pumps and fans, are used to increase the pressure of the fluid. So the fan increases the pressure of the gas slightly, but it's mainly used to mobilize gas. And a compressor compresses the gas to very high pressures, and pumps do the same as compressors, but it's usually for liquids. Okay. Now, in this case, we have an example of T1. I just don't want to put a figure and not explain it. And then we have something coming out, P2. You've increased the pressure and thus the temperature. Remember, in this case, we have air. And in this case, we have Q coming out, and we have a shaft, so we have work. This is M dot, which would be the same going in than going out. But the main thing here is that because we're talking about air, you don't look in the tables for water. You look in the tables for air. And whenever you look at the Q out, then you need to look at the specific heat of air under the tables at the back of the book. But just for notation, because I know in the homework there will be a problem on air, but just one problem. The others will be with steam. So let's leave this on hold for now, but let's see how what is the expression that we will come up by first looking at the general expression. Remember, that's a good habit to always write it down and then start eliminating according to what you think is happening. So let's take a look here at what expression we will obtain here. And I should have given you some piece of information that the change in potential energy is approximately 0, because that means it's the same, and I should have told you that the change in kinetic energy is approximately 0 as well. So what we have is in this situation, we have Q going in or heat going in? No. Do we have work going in? Yes. Do we have Q going out? Yes. Do we have work going out? No. Do we have changes in velocity? Well, this tells me this kinetic energy does not change, so this cancel out, assuming the velocities in and out are the same, and the potential energy is also zero, so this will cancel out. So what I'm left with is W in plus, and then I only have one inlet and one outlet, M1H, 1 equals Q out plus M2. So I'm going to call this as number 1 and this is 2. So that is the expression that I have, which will be used for turbines and compressors. There's always going to be these losses in here, so that's why. And then if you have a compressor or a turbine, then you have work going in or out, right? In this case, we're saying there's work in, but then you would change the sign if it goes the opposite way. So that's a generic expression. This is just a summary of what we obtained. Then throttling valves are flow restricting devices, and the purpose is to cause a significant pressure drop in the fluid. Sometimes they increase the pressure, so it's really to induce a change in pressure. And we have seen those, and you will see them in chapter 7. There's some of these valves. So I'm going to develop this. I say group activity, but since we're changing things a little bit this semester, I want you to really understand how to develop these equations and how to derive them using the main equation and then canceling. So for a throttling valve, this is what you have, and the one thing that's important is that I mentioned that the valve is insulated, or it's an adiabatic, and that the change in potential energy is insignificant, and the change in kinetic energy is also insignificant. So there's no Q going in and out. I don't see any wire, any shaft, any spring, so I don't have any work. And they tell me that the change in kinetic energy is 0 and potential energy is 0. So what I have here is M1 is 1 equals this is M dot H2, assuming that we have 0.1 and we have 0.2, and then M1 equals M dot, conservation of mass, so H1 equals H2. This is the derivation. In the case of mixing chambers, we have M1 and M2, so we will have like hot water and cold water, and we call it a chamber, but it can be a T elbow or a Y elbow. Okay, we just represent it as a mixing chamber. And so we have hot water and cold water being mixed, and then we have the mixed water temperature that's coming out, and this is an example of a shower or a faucet when you're combining. So whenever we look at the adiabatic mixing chamber, we have cold water and hot water going in and warm water going out. I'm saying there's no significant changes in velocities and elevation, and it's an adiabatic mixing chamber. So that means that Q equals 0. And remember what we said about Q, that Q is 0 doesn't mean that there's no change in temperature. It just means that heat is not crossing the boundary. And then we have no significant changes in velocity and no significant changes in space. All this is going to be 0 for sure. So whenever we look at the derivation, remember we said no Q in, no Q out, no work in, no work out. We will have 2 inlets and 1 outlet. So we will have M, and let's call this 1, and this 2, so, and then the outlet would be 3. So we have M1, H1, but then also the changes in kinetic energy and potential energy are not significant, so we can eliminate this. So we have M1, H1 plus M2, H2 equals M3, H3. Also, in this case, we have the conservation of mass, and what we have is that M1 plus M3, and M2 equals M3. So, in this case, we will need both equations to solve this type of problem. And the problem can be about calculating what's the enthalpy or what is the final temperature. So with these 2 expressions, you'll be able to solve the problem. This is, again, the final expression. So this example 6.9 is an example of a mixing chamber. Please review it, study it, on page 207. We just mentioned briefly heat exchangers that are devices of 2 fluid streams. We're trying to cool a fluid. In this case, for example, we have fluid going through the heat exchanger. It's fluid A, started at 20 degrees Celsius, and we want to warm it up to 60. So what you have is this chamber that has a higher temperature to increase the temperature of the fluid along the pipe. You could have the opposite. You could want to have, instead of a heat exchanger, a cooling system. And in that case, you would have, for instance, your cooling system where you have your flow with the pipe going through it, and then you probably have your 50 degrees Celsius, and you want it at 20 degrees Celsius, and then so you would add water at 15 degrees Celsius, for example. And so instead of passing the pipe through a system that has heat, then you have colder water. So that would be a cooling system. And usually cooling systems, contrary to the heat exchangers, have a lot of pipes. So it would be like looking like a radiator from a car, but then it's immersed in colder water. So in summary, we've completed this. We've done the mass involving flow rates, steady flow processes, and we talked about incompressible flow. We defined the energy transport by mass, and we did the energy analysis for vessels and diffusers, turbines and compressors, bottling valves, and mixing chambers. The heat exchangers and pipe duct flow we did not discuss, but I just wanted to give you a taste of all this. I hope that this has been helpful. I believe this is the last slide, so as usual, thank you for getting to this point, and email me if you have any further questions. Have a great day.